Hello everybody, this is Mr. Strager, and today we're going to be talking about Big Ideas, section 2.5. Now, in class, we actually didn't start off by talking about the notes. We started off by talking about a little bit of a warm-up. Here's the deal. Section 2.5 is tough. I would definitely call it a little bit more than tough. It's very difficult for many people to get the first time around. So I want to make sure I can do everything in my power for us to feel comfortable with the content. So first things first, here's what I want us to do. I want you to try to give me a number that is less than 7 and more than 3. Take a second, pause the recording, and see what you get. See if you can come up with all the numbers that are less than 7 and more than 3. Hopefully we pause the video and try it out. So there are a lot of answers to this, of course, because there are a lot of fractions and decimals that we could do. But I want to just talk about the whole numbers. Let's take a look at the number 3. Is it possible for 3 to be less than 7 and more than 3? Well, if it's the less than 7 part, no problem. But 3 is not more than 3. So unfortunately, we can't start there. But what about 4? 4 is less than 7 and more than 3. Same with 5, same with 6. So ask yourself, what about 7? Well, 7 wouldn't work either because 7 is not less than 7, but it is more than 3. So the whole numbers that work for this are 4, 5, and 6. But of course, there are plenty of other numbers that work for this as well that we have to keep in mind. For instance, halfway in between 3 and 4, we have 3.5 or 3.5. Is 3.5 bigger than 3? Yeah, and it's less than 7 too. You could even go as far back as 3.000001, something that is so tiny. It is so barely above 3, but it is more than 3 and less than 7. So it fits both rules. Let's change up the rules slightly though. Now, I want you to give me a number that is either greater than 12 or less than or equal to 4. Again, I'd like you to pause the video real quick and see if you can give me a number that is either greater than 12 or less than or equal to 4. All right, if you picked a number that was less than or equal to 4, the highest number you could have picked was 4, right? Because we have this or equal, it means that 4 totally could work for this, but also all the numbers that are less than 4. So your 3, your 2, your 1, 0, -1, and all the fractions that are less than 4 as well. Let's say you pick the other direction though. Because I said the word either, you could have also decided to give me numbers that were greater than 12. So you could have given me something like 13 or 14 or 15. Again, 12 wouldn't work because 12 isn't bigger than 12. But you can keep on going up and up forever if you really wanted to. Here's the deal. Previously, we kind of talked about a very small section of numbers that would work. We picked numbers that were in between 3 and 7. So it's a much tinier selection. Here, these numbers can go on forever and ever and ever. So we say that when you have a choice between either one, it ends up working out. All right, so let's go on to the next slide. This is going to be a little bit of a challenge, but I think we can handle it. I want you to give me a number that is greater than or equal to 3, and a number that is less than or equal to 3. I want you to try this out on your own. Pause the video if you need to, and feel free to give it a stab. This one is a little bit trickier, just because we have to deal with a lot more. So let's take a look. In red, I'm going to write the numbers that are greater than or equal to 3. I'm just going to write 5 of them. So 3 is equal to 3, so that works. 4 is greater than 3. 5 is greater than 3. I'm only going to write 4 after all. I changed my mind. So 3, 4, 5, 6, but you could continue on forever if you wanted to, because those are the numbers that are greater or equal to 3. What about those that are less than or equal to? Well, the highest number that we'll be able to get is 3, right? But all the numbers less than that, like 2 and 1 and 0, those all work as well. Again, these 3's are in these lists because we have the or equal to clause here. Since both versions of the problem, both inequalities, can equal 3, 3 ends up actually only being the only number that works for this problem. The only number that is greater than or equal to 3 and less than or equal to 3 is 3. After we talked about this, we went on to discuss something like this: graphing inequalities. So what we would do is we would start off by graphing one inequality at a time. Then we would go ahead and see where they overlap. Let's take a look at x is greater than or equal to -1. Since we have that little bar underneath our greater than symbol, it means that it's going to be a closed circle. And since we're talking about -1, closed circle is at -1. Now we need to decide which direction our arrow should go. Should it go to the left or the right? To decide this, I always recommend plugging in a number for x. So think of a number real quick in your head. The number that I picked was 2. So if you pick 2, you're probably a mind reader. But is 2 greater than or equal to -1? Well, in this case, yes, it is. Since 2 is a solution here, we want our arrow, wherever we place it, to go through 2. Well, 2 is all the way on the right-hand side, so our arrow should go towards the right. But let's say you didn't pick 2. Let's say you picked something that doesn't work, such as, I don't know, -4 or -3 even. -3 is not greater than or equal to 1. So we agree that -3 is not a solution. Since it's not a solution, that means our arrow can never touch -3. So to avoid it, it goes in the opposite direction. No matter what, our arrow will go to the right. Let's do the same thing with the blue. It says to graph x is less than or equal to 3. Well, 3 is right here, and since it's less than or equal to, we want to make sure it's a closed circle. From here, we want to draw our arrow. In this case, when you test out numbers, you'll find that our x values are all to the left. One value that I test out that worked for this is 0. I love using 0 for these because 0 is usually going to be available. So 0 is less than or equal to 3, therefore our arrow has to go in that direction. Now comes the tricky part. We need to highlight the area where both lines overlap. Many people during class highlighted the area like this, which you can see the overlap. But I asked a question to them. What about the areas that include our endpoints? In other words, should -1 and +3 count as areas where both lines overlap? Well, let's think about it. The areas where they overlap are the places where x is a solution, x has a solution for both of them. So for instance, right here at x equals 1 is a solution that works for x has to be bigger than or equal to -1, x has to be less than or equal to 3. It also works here at 0 or here at 1/2. It works everywhere that is shaded in here. What about at -1? Well, since we said that x could equal -1, and -1 is definitely less than 3, it absolutely does work. So in total, your shaded area shouldn't just be this middle portion here. It should be the entire area encompassing -1 through 3. All right, let's try something a little different. Here, I want us to graph x is greater than or equal to 3 in red, x is less than or equal to 1 in blue, and I want us to figure out where either line exists. Well, let's start with our endpoints, just because that's the easiest. And if x is greater than or equal to 3, is 4 a solution? Yeah, 4 is greater than or equal to 3, so we're going to draw an arrow through it. Let's do the same thing with the blue. X is less than 1. Would 4 be a solution to that? No, 4 is not less than or equal to 1. So the arrow goes the other way to avoid the number 4. Finally, the question asked us to highlight the area where either line exists. Well, we already discussed that the line exists at the endpoints when it is filled in, and we mentioned that it's going to exist everywhere the line is. So here are all the solutions. See what I mean when I said that an either statement usually has a lot more solutions? Here, everywhere the yellow is, there are solutions. And if you think about it, it might be even easier to think about parts that don't have solutions. For instance, could x equal 2? Well, 2 is not bigger than 3, so it wouldn't work for the red. And 2 is not bigger or less than 1, so it wouldn't work for the blue. That's why 2 is not a solution. This last one, oh, actually, that is the end of this presentation for right now. So we did a couple more problems like this, but overall it was just practice. Keep in mind, however, that any time you end up with something that is just greater than or less than, then things are a little different. Let me give you an example. Let's cross off these symbols here and say that instead we had x is greater than 3 and x is just less than 1. Well, our solutions would be about the same. The problem is now we would use open circles. As a reminder, we use open circles to show that something is not a solution, but that the line starts there. Well, our arrows are still going to face the same way. We didn't change those directions. We didn't change the direction of our inequality symbols. But now when we highlight, we have to remember that the line actually doesn't exist at 1 or 3. It doesn't. 1 and 3 are not solutions because 1 is not less than 1 and 3 is not bigger than 3. So when you highlight, it's going to include everything except for 1, 2, and 3. That was the presentation section of things, but then we shifted over to the notes. For that, I'm going to change over to my camera real quick. Oops, I apologize. It's probably going to look weird on your end, but maybe it'll look a little bit different now. Oh my. Clearly, I need to make sure everything is in order here. Let's try it one more time. If it doesn't work, then I'll be upset. So if I go and I share my presentation, I go and I share my second camera. Aha, I don't need to be upset. So then we started the notes. First off, a compound inequality is an inequality, surprise, surprise, created when two inequalities are joined. So we put two inequalities together using the words and or. And these two words are extremely powerful for this section. Let me give you an example of when the word and might be used. So if I gave you a problem like this, x is greater than 2 and x is less than or equal to 5, this is a case where we are looking for both rules to be true. And is just a fancy way of saying, hey, we want both rules to be true. So when we graph this, we're going to follow a very special procedure. First things first, of course, we have to make and label our graph. And for this section, instead of having our endpoints in the middle, what I'm going to recommend is that you make your number lines big enough that you have one number to the left of your lowest endpoint and one number to the right of your highest endpoint. In other words, you want it to be able to fit your endpoints plus one on either side. What do I mean by this? Well, if we look at this first inequality, 2 is our endpoint. Should it be an open circle or a closed circle? Well, it should be an open circle. The rule is if it doesn't have an equals bar underneath, we want it to be an open circle because x can't equal 2. It's just bigger than 2. What about this one? Well, we're going to have an endpoint at 5. And it's going to be a closed circle because it does have the bar. From here, when you have an and statement, we're looking for the area that makes both inequalities come true. So we'll make x is greater than 2 true. Well, 3 is greater than 2, 4, and 5, and 6, and 7, and 8, and 9, and 10, and 11. What about x is less than or equal to 5? 5, and 4, and 3, and 2, and 1, and 0. When you have an and statement, you're looking for the area that both inequalities work in. In other words, we're looking for the place where both arrows will exist. I wouldn't want you to do this on your paper, but you could make even sort of like a very faint arrow for each inequality and see where they overlap. Well, it looks like both arrows exist everywhere in between the two. That means that your solution is going to look like this. And in general, all of your and solutions will either look like this, or will have both circles filled in, or will have 2 open circles. It's going to kind of look like they're connected by a little line segment. That's because that's the area where both inequalities work. However, this is a little bit of a mouthful to say. X is bigger than 2 and x is less than or equal to 5. In conversation, we would probably say something more like x is in between 2 and 5, including 5. Well, how can we represent that mathematically? What we're going to do is we are actually going to take x and put it in between 2 and 5, since x is everywhere in here between 2 and 5. From here, we're going to add inequality symbols that will make this work. So let's start off with the easy one. How is x related to 5? Well, it says up here that x is less than or equal to 5. And we can see that from our graph too. X could be equal to 5 or it's less than 5. But what about 2 and x? This is the tricky one because you might be tempted to just take the symbol from up here, the greater than symbol, and put it down here. But then that would say 2 is greater than x. Is 2 greater than x in this case? Well, no. 2 is actually the lowest point that x could be, and it can't even be 2. It's always just bigger than 2. So keep in mind that you can always flip your inequality symbols to show this. X is bigger than 2 is the same as 2 is less than x. Well, that looks a little more familiar to the situation we have down here. And we want to write it this way as well. When you write out your and statements, all of your inequality symbols should be facing towards the right because we're going from lowest to highest. So all your symbols should keep on going towards those highest numbers. And that's how we can express our compound inequality for and. Don't worry, the or statement is a little more simple. Let's look at the or statement. If I told you that x is less than 2 or x is greater than or equal to 5, this is going to look very similar but different to the last one. We got to think, did our endpoints change? Well, no. It looks like we're still using 2 and we're still using 5. Will the state of our circles change? Well, no, we're still going to have an open circle at 2, and we're still going to have a closed circle at 5. The difference here is now we're looking for solutions when x is less than 2, or we're looking for solutions when x is greater than or equal to 5. Either one will work. So that means when x is less than 2, it'll go down to 1 and 0 and -1 and -2. Everything that way will work. But x is also going to be fine when it is bigger than or equal to 5. So 6 is bigger than or equal to 5, and so is 7 and 8 and 9, and so on and so forth. So our arrows are going to face opposite directions. The only things that won't work for this are the numbers 2, 3, and 4. 2, because 2 is not less than 2. 3, because 3 is not less than 2 or greater than 5. And 4, because 4 is not less than 2 or greater than or equal to 5. The fun part about or statements is you don't need to write anything special for the solution, nothing like this. You would just write out both inequalities. X is less than 2, or x is greater than or equal to 5. In general, we like to keep it in this order, but you don't need to. It's just sort of like reading from left to right. The way that I recommend remembering these is when you have an and statement. In other words, when you're looking for the intersection of two lines where they cross, you're going to end up with something that looks a little cross-eyed. If you're looking for something where it is either in one direction or the other, you can think of it like two eyes that are looking in different directions, kind of like a lizard. This is how we can remember and or. Let's put some of that knowledge to the test. I want you to try looking at problem number 2. D is less than -2 or greater than or equal to 2. Try it out on your own and check with me once you're done. So we should have seen that if D is less than -2, first things first, we need to have 2 and -2 on here. Again, I recommend having at least one number written down that is below your endpoint. Since -2 is our endpoint, as long as -3 is somewhere on there, we're fine. And as long as, since 2 is our endpoint, as long as +3 is on there, we're fine. So let's take a look at this. If D is less than 2, we want to put, or -2, we want to put an open circle at -2, because it's just less than, not equal. Keep in mind, this is an or statement. So we know that our lines are going to face opposite directions. If D is less than -2, then D will go in this direction. The other endpoint is 2, and since it can be equal to 2, we use a closed circle. Finally, since D has to be greater than or equal to 2, we want it to be the numbers that are bigger than 2, like 3, 4, and 5. So we end up with our lizard eyes situation. At this point in time, the lesson for day 1 of the notes is finished. So if you've only completed the day 1 lesson, stop here and try out the homework. But if you're here for day 2, stick around. We've got a little more to talk about. If you're still listening, that either means you have me on in the background, in which case, well, shame on you. It's nice to listen to math, but come on, you gotta be watching this too. However, if you are still here for lesson, or I should say day 2, you have come to the right place. In day 1, we talked about problems like this. Problems where we just have our x sandwiched in between 2 endpoints, or x being in 2 different places. But we know that this is algebra 1. And in algebra, remember the definition of algebra? The fixing of broken pieces? Well, we're going to see some broken pieces here today. What would you do if I gave you the following inequality? If I gave you the inequality, -3 is less than or equal to x plus 4 which is also less than 12. Uh-oh, now we've got some math to do. Here's the deal. We know how to solve something that looks like this, right? If we didn't have this other inequality symbol, we would just subtract 4 from both sides and get x by itself. What if we had just the less than 12? Well, the steps would be the same. You'd still want to get rid of this plus 4, right? So you would subtract it from both sides. Wouldn't it be nice if we could just do that step as simple as that? Well, we can. As it turns out, these two inequalities still exist, even though we put them together, just like in day 1, how we put together x is greater than 2 and x is less than or equal to 5. These are still two inequalities, just combined together into one joint inequality. So wouldn't we be able to take it apart as well? It turns out we can. To take apart an and inequality, I literally take my fingers and I put it over one of the inequality signs and whatever is on the other side of the inequality symbol. So I'm covering up less than 12. This right here is one of our inequalities. So we rewrite it. -3 is less than or equal to x plus 4. Can you figure out what the other inequality is going to look like? Well, I always recommend taking my fingers and covering up the other inequality symbol. We're left with x plus 4 is less than 12. So that's the other inequality we're trying to solve. Keep in mind, you don't actually need to split these every time, but I'm going to show you this method first. So let's look at the first problem. Like we mentioned, what can we do to get x by itself? We want to subtract 4. Because, as a reminder, x is not alone. We want to get x alone. But what's attached to the x? It's plus 4. How do we get rid of plus 4? We do the opposite, which is minus 4. That's why these will cancel out, giving us just the x. Our symbol stays the same because we didn't multiply or divide by a negative. Remember that rule? And -3 minus 4 is -7. So -7 is less than or equal to x. Okay, let's take a look at the other one. X plus 4 is less than 12. Well, hang on a second. It's still the plus 4 that's attached, right? So it turns out the steps are going to be the same. To get rid of plus 4, we subtract 4 from both sides. These cancel out, giving us x is less than 8. So our solutions are every value of x where -7 is less than or equal to x is less than 8. In other words, this is still an and statement. But our solution is -7 is less than or equal to x and x is less than 8. Keep in mind, it's an and statement because of how it's connected here. When x is in the middle of two endpoints, it's an and. When our x is on the outside, it's an or. But that looked like a lot. And I'm sure that some of you are getting flashbacks from Unit 1, where we did the splitting with the absolute value symbols. Don't worry, we'll still do that in the next section, but there is a faster way of doing this. And I almost always recommend it if you know what you're doing. Keep in mind that the step we did here was the same in both problems. That will always be true. The step is always going to be the same to get x by itself. We subtracted 4 from both sides of the inequality symbol. So we subtracted a 4 from the x plus 4 side and from -3 side. We subtracted it from the x plus 4 side and the positive 12 side. We can, instead of doing it in two separate equations or inequalities, do it all at once. The difference is, instead of having a two-sided equation or inequality like we always have been, I see two inequality symbols. So this is a three-sided problem. I know, it's a little bit complicated, but if you can remember it, it makes it faster. So when you subtract 4 to get x by itself, you got to subtract it from every side. Well, here's the left side. We already subtracted from the middle side. And 12 minus 4 will give us the right side. That gives us the compound inequality -7 is less than or equal to x, which is less than 8. This big statement down here, -7 is less than x and x is less than 8, can also be rewritten in the same way. -7 is less than or equal to x, which is less than 8. So this, no matter which method you use to get it, will be our answer. Let's try one more, and let's make this one a multi-step. We know the multi-steps can be a little bit crazy. Let's say we had the following OR statement this time. Let's say that I knew 2x plus 3 was bigger than 5. Or the other alternative is, instead of 2x plus 3 being bigger than 5, I just had x divided by 3 minus 1 is less than, let's do -2. Well, this is going to be a tough one to solve, but keep in mind, we can always solve it separately. Because unlike in an AND statement where you would just have one x term in the middle, this one, an OR statement, has two x's. Unfortunately, we do need to split it. So even though it's easier to write out your answer as just an OR statement instead of having to do all this nonsense, it does make it a little trickier to solve. Let's solve this first one. 2x plus 3 is greater than 5. Well, we want to get x by itself. The problem is there are two things attached to it. Multiplying by 2 and adding 3. Anytime you have to decide which to do first, you always need to think about reverse Pemdas. Reverse Pemdas tells us that we want to get rid of addition and subtraction first. So let's get rid of the plus 3 by subtracting 3 from both sides of our inequality. These cancel out, giving us 2x is greater than 5 minus 3, which is 2. Then to get x by itself, we want to get rid of times 2, so we divide by 2. Pause for a second and consider, do we need to flip our symbol? Well, the answer is no, because we divided by a positive number, not a negative. So x is greater than 1. But we're not done. We got to do the other side too. X divided by 3 minus 1 is less than -2. So to solve this, we would want to, again, consider what do we do first, division or addition? Or sorry, division or subtraction. We get rid of subtraction first because reverse Pemdas. So we add 1 to both sides, giving us x divided by 3 is less than -1. To get rid of dividing by 3, we multiply by 3. Do we need to flip? No, because 3 is positive. So x is less than -3. Our final answer is x is greater than 1 or x is less than -3. Let's try just one more, and this one is going to be on page 52. Specifically, I want us to take a look at the one down here at the bottom, number 10. Number 11 you could do by itself as well, but number 10 I like for a different reason. First of all, is this an AND inequality or an OR inequality? Well, it's an AND because our x is sandwiched between two endpoints. Now, in order to get x by itself, we're going to need to do a little bit of work. First things first, there are two ways of solving this problem. Either way, the first thing we should deal with is this 1/3 that's outside of the parentheses. If you use reverse Pemdas, you would divide by 1/3, but dividing by 1/3 is messy, so you would multiply by the reciprocal, meaning you would multiply -8 by 3 and 12 by 3. But I want to take a different approach for this one. I want to take the distribution approach, which many of you take when we see these problems. When we distribute, we're multiplying 1/3 to everything in the parentheses. So we end up with -8 is less than or equal to 1/3 times 6x is 2x. 1/3 times 24 is 8. And that's still less than 12, or less than or equal to 12. Now we can actually simplify this, but we have to do the same thing to both sides, or I should say to all sides of our inequality. When I say all sides, I mean physically draw a line down your inequality symbols so you know what sides you're talking about. In this case, there are three sides. There's a 2 being multiplied to our x and an 8 being added to it. So which do we get rid of first? We get rid of the +8 because of reverse Pemdas. But if we subtract 8 from the middle, we have to subtract 8 from the left side and the right side too. That'll give us the following compound inequality. -8 minus 8 is -16. -16 is less than or equal to 2x, which is less than or equal to 12 minus 8, which is 4. Well, now what do? Now we want to get rid of the 2 in front of the x. How do we get rid of multiplying by 2? We divide by 2. -16 divided by 2 is -8. We didn't divide by a negative, so all of our symbols stay the same. X is by itself, and 4 divided by 2 is 2. To graph this, I'm going to use the number 9 graph here, just because I ran out of space here. Oops. But we start off, as always, by putting down our endpoints. So we know our endpoints have to be 2 and -8. But we have 10 numbers on our scale here, so it has to fit. The only way it's going to fit is by putting 2 here and -8 here. In general, though, I always recommend having at least one number on the outside of these, just so that it's clear where your lines are, where they start and end. It's just that for this particular problem, the numbers work out in a weird way. So they actually touch the extremes. -8 is an endpoint, and because we see that this is an equals bar underneath, it is a closed circle. 2 is also a closed circle because it has an equals bar in between the x and the 2. And because x is everything that's in between these two, we draw our line. Now, just one last thing. I know I said that this was going to be the last problem. If you ever have a problem where it turns out we have a negative that we're dividing or multiplying, like in this one, to get rid of the -5 times g, we would divide by -5. Our rule still applies. You still need to flip the inequality symbols. But which ones? You flip all of them. So we go from having greater than or equal to symbols to less than or equal to symbols because we divided by a negative. Then you would finish off the problem at normal because -3 is less than or equal to g, which is less than or equal to 2. And notice how when you flip your symbols, all the numbers end up in the right order. It ends up going from least to greatest. Told you it'd be useful. All right, thank you so much, everybody. Feel free to try out the homework, and if you have any questions, just let me know. Have a great rest of your day, everybody.